Welcome to the Problemas channel, season 2, episode 21. The episode which I have titled Heavy 5-Digit Perfect Squares for the reasons that I will explain in a moment. But before I do that, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section find the episode titled The Problemas Channel How To. Watch that episode in its entirety, follow all the instructions given in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E21, working exclusively in base 10, we're asked to compute the number of 5-digit perfect squares that have the following property. If 1 is added to each and every digit of that perfect square, yet another perfect square results. So how did I come up with the name of this episode, or the title of this episode, Heavy 5-Digit Perfect Squares? Well, I guess that I have a little bit of a physicist left in me still. So let us assume that to each digit of a 5-digit perfect square, let's say 1, 2, 3, 4, 5, we represent each digit of a perfect square with the square befittingly. We add 1, and how do we model adding 1 to each digit? Well, plus 1, plus 1, plus 1, plus 1, plus 1. Let's say we add another 1 unit of mass weight. So by doing so, we make each and every digit of our perfect square heavier. Consequently, we do the entire square heavier. And what is the result of this maneuver supposed to be? Well, the result of this maneuver supposed to be yet another, let me maybe draw it in some fancy way, supposed to be yet another square, and we are asked to compute the number of such 5-digit perfect squares. As I promised at the end of the previous episode, I will use this mathematical problem as a fodder for the explanation of how the reduce and conquer problem-solving approach works. As a quick reminder, so far between the previous season and this season, we looked at how the following problem-solving approaches work: transform and conquer, reinterpret and conquer, reverse order, space-time, equation, and now we will study how the reduce and conquer problem-solving approach works. Also, the name is completely arbitrary. It's mine. If you have a better idea, be my guest, by all means. Share your ideas with us and with our community in the comment section of this video. But a different but equivalent name for that approach that also can be used is scope reduction, because as you may imagine, this specific problem-solving approach has its close cousin, and it's called scope expansion, as another problem-solving approach that we will study right after this one. And consequently, using this template over here, we can say expand and conquer is another name for that problem-solving approach. And now we want to understand how does the reduce and conquer, or scope reduction, problem-solving approach works. Personally, I have learned about the scope reduction or reduce and conquer problem-solving approach from the book by Gregory Poya shown over here, How to Solve It. If you're serious about doing anything more or less serious in mathematics, theoretical physics, and computer science, it is a very good idea to read this book, How to Solve It by Gregory Poya, at least twice or thrice. And Poya also has another, it's called a book, but it comes in 2 tomes, in 2 volumes. The first volume is called induction and analogy in mathematics. And the second volume of that book is called Patterns in Plausible Inference. It also relates to mathematics, also highly recommended. It will take you several months to work through the material presented in this book, but you will never regret it. Every information that Poya gives in this book is absolutely valuable. So now we want to understand how the scope reduction or reduce and conquer problem solving approach works. For demonstration purposes, let us say, let me grab some white chalk, that we are working with a problem that is so difficult that we cannot solve it at first attempt, or at first blush it seems to be very difficult to solve. For demonstration purposes, I will designate such a problem with a geometric point right here in white chalk. We will call this problem also, let's say, P1. This is our difficult to solve or original problem. Then, according to our collective mathematical, pedagogical, and problem-solving academic wisdom, the claim here is the following. If it is the current problem, P1, that we cannot solve, then there exists a simpler, these things are so important, I'll write it down over here, simpler, related problem that we also cannot solve. Find that problem and try to solve it. Here it is very important to understand that for the scope reduction problem solving approach to work, it is absolutely crucial that the problem over here that I will portray in a minute, that will be the next in the reductive chain, possesses these two specific properties. The problem is simpler and related. We will designate that problem with another point right here, and I will name it the problem P2. So according to the scope reduction problem solving approach, if it is the current problem P1 that we cannot solve, then there exists a simpler related problem that we cannot solve. Our objective, as per the scope reduction problem solving approach, is to find such a problem P2 and try to solve it. So let's discuss these properties over here a little bit. What does it mean for a problem such as P2 to be simpler than the original difficult problem such as P1? This is actually not as easy to define and to explain. It's easier to see these things in action, but in some sense, a simpler problem is basically a problem that is lower in its perceived difficulty rating. And I understand this is not a very algorithmic description, but again, these things are easier to see in action than give a short, concise, and all-exclusive definition that all the mathematicians in the room will agree on. So here, the problem P2 should possess the first property, should be simpler than the original or lower in its perceived difficulty rating. And related, what does related mean? Related means that the problem P2, that is simpler, should preserve the technical essence of the original problem P1. So these two properties must be available in the problem P2 as a transaction. They both must be present and neither one can be absent. For example, if we did not come up with the simpler problem but came up with the related problem, then again, what is the point? We're not gaining any tactical advantage because the problem P1 by assumption is so difficult that we cannot solve it. Likewise, if we came up with the problem that is simpler but it's not related, and the problem that deals with something else, that yes, maybe we'll be able to solve this simpler problem, but our goal is to solve this original problem. And because there is no technical connection between the problem P1 and the simpler problem P2, then again, what is the point? We will be solving some other problem, but not this one, the one that we want to solve. Consequently, it is important to understand that for the scope reduction problem solving approach to work, we need to search for and find a problem that has both of these properties locked in at the same time. I will put down over here and simpler and related. In other words, the problem should be lower in its perceived difficulty rating, and it should preserve the technical essence of the original difficult to solve problem. We will portray this process of descent with red arrows over here. And now, once we understand how the first step in the scope reduction problem solving approach works, we apply that step recursively on each problem. If we cannot solve the problem P2, which is simpler and related, then again, according to the current pedagogical, mathematical, and academic wisdom, there exists yet a simpler and related problem that we cannot solve. Find that problem and try to solve it. So I will portray this problem with another point. We will name that problem P3. We will portray the process of descending down the perceived scale of difficulty rating with red arrows like so. And the problem P3 also should possess these two properties. It should be simpler yet than the problem P2, but it has to retain, it has to preserve, or it has to be true to the technical spirit of the original problem still. And now we understand that this process can be applied recursively to each problem. So I'll designate this process of reduction of the perceived difficulty rating like so, with the dashed line, and at some point we will arrive like so at the problem that we will name Pn-1. Let's say, assume that is all this problem over here is simpler yet than all the previous problems. It still preserves the technical spirit of the original problem. We cannot solve it, and we arrive at some point at the problem to which I will refer as Pn. And the interesting question over here is the following. Will this process, or can this process of reduction of the perceived difficulty rating of the original problem run indefinitely? Can it run as long as forever, let's say? Or must that process terminate in a finite number of steps? This is an interesting question. It should probably be debated in a separate episode, but for now we will assume that the problems that we are dealing with, they only have that much difficulty juice in them, so to speak, that at some point this reductive chain of stepping from the original difficult problem to a simpler one terminates in a finite number of steps, designated here with Pn. And that means that the next step will either yield not a problem, or perhaps an axiom or a statement that can be taken as true at its face value and become a rule of the game. So in a finite number of steps, let's say we arrive, in this case, in this interpretation, we arrive at a problem shown over here as Pn, such that we will refer to this problem as the rock bottom, simplest possible, but still related problem that can happen under these conditions of the problem P1. Here, what happens next determines the fate of our ability to solve the original problem. If we cannot solve this problem Pn, which is the rock bottom, simplest but related problem to the original one, then obviously there is absolutely no hope that we can solve the original problem that is way more difficult than this one, simplest in some sense possible problem that is related to the original. However, and in this case, if we cannot do that, we give up, we have to seek help elsewhere. But let us say we can solve this problem. Here we have a reason to celebrate, and I will depict this idea that we managed to solve this problem. So here I'll write even the word solved. We managed to solve this problem, so this problem is solved. Now the idea is the following. Let's say we managed to solve this problem. We'll also designate it as Pn. The idea here is the following. Just because we managed to solve this problem doesn't really mean that we will gain certain useful tactical and fruitful insight into what is really going on in this. As such, we have to be careful with the wording. If we manage to solve this rock bottom simplest related problem in such a way that we have or managed to gain certain insights or certain interesting tactical or strategic information about what is going on with this particular problem that is over here shown as P1, then we may and we should take that gained or gleaned insight into the technical essence of what's going on in the simplest problem and try to solve the previous slightly more difficult problem in our difficulty rating. And I will portray this process over here of descent this time with a green arrow. So let's say we not only solved the simplest possible problem, but we also gained certain insight that allows us to take on the previous slightly more difficult related problem. Can we solve this problem over here? Well, using the insight, tactical insight gleaned during the solution of the simplest problem Pn, we attack the problem Pn minus 1, and for demonstration purposes, let's say we solved it. That means that, again, we may or may not glean or gain certain more insight, but again, for demonstration purposes, let us assume that we did. So now we possess a cumulative wisdom that we gained during the solution of the simplest problem Pn and during the solution of the next slightly more difficult problem. Armed with this cumulative knowledge and wisdom and insights, we step up to the previous problem. And again, let me show you, yes, in dotted line. Let's say we take on the previous slightly more difficult problem and on and on and on. And let's say here we come to the same problem P3, and we manage to solve the problem P3 in such a way that we gain even more insight. And using all the insights that we have accumulated so far, we take on and succeed at solving the problem P2, shown over here. And again, for demonstration purposes, let us assume that all this cumulative wisdom that we managed to uncover during the solution of this entire chain of related problem is such that we can take on the original problem, P1. And again, for demonstration purposes, this is of course an idealistic situation. We finally come up to the original difficult problem P1, and using the aggregate or collective combined wisdom that we gained during the solution of the chain of the related problems, we take on the problem P1, and hooray, we managed to solve it. And this terminates, so to speak, the description of the reduce and conquer or scope reduction problem solving approach. And once you gain understanding of how that process works, you may even continue constructing even more difficult problem, but this is already extra for experts. And we all should understand that the description that I gave over here is idealistic, of course. Your mileage, your specific journey over this or that problem will definitely vary. For example, in some cases, you will descend maybe only once or twice, solve the slightly easier or slightly less difficult problem, and then climb all the way back up and dig yourself out of the hole. Boom, done. Very nice. Sometimes you will descend all the way down, solve, for example, the simplest problem, then the one previous, then the one previous to it, slightly more complicated, boom, and you'll get stuck over here and you will never be able to move up. Or you can come closer and closer, but still you will not be able to reach the solution of the original more difficult problem. These scenarios, of course, are way too numerous to describe, but an idealistic chain of reduction, solving, and then unreduction or taking on slightly more and more difficult problems in carefully calibrated increments may lead to success. Now that we understand how the description of how the scope reduction problem solving approach works, I already know the popular question that comes up from many students who take on this specific problem-solving approach. Roman, how do we know that a given problem over here, like P2 or P3 and so on, is simpler and related? What is the criterion? How do we simplify a given problem and still preserve the technical essence of the original? This is a very good question. Again, I think it's very difficult to give a short, concise, all-inclusive definition of what exactly does it mean to simplify a mathematical problem yet keep its technical essence intact in such a way that all the mathematicians in the room will agree on it, and that definition will be very algorithmic and will tell you exactly, in this problem do this, in that problem do something else. This is not the case, unfortunately, and one of the best ways to understand and see how the scope reduction problem-solving approach may work is to begin solving the problems using this approach. And this is exactly what we will do with the mathematical problem S2E21. Now that we understand how the description of the scope reduction or reduce and conquer problem-solving approach works, let us try to apply that problem-solving approach to the mathematical problem S2E23. Here, on the one hand, whenever you learn anything in mathematics, theoretical physics, and computer science, that something sounds scary and very important at first blush, but then when you step up closer to that something and begin working with it, trying to understand it and think about it, then eventually you realize that, it's not really that scary, and once it becomes part of your bone marrow, you probably will think it's not really that important. So that is an interesting property of technical information. On the other hand, I already know, as I said before, that most of the students who take on this problem-solving approach will ask the following question: Roman, modern mathematics is so wide, tall, and deep that even simple mathematical problem statements have too many levers to pull, knobs to twist, and buttons to push. So how do we know which lever to pull, button to press, and something else to do in order to change the original problem in such a way that it becomes simpler yet related? That is a very good question. And again, like I said before, I think it's very difficult or very challenging to come up with one short, concise, and very algorithmic definition of what does it mean to simplify a problem yet keep its technical essence in such a way that all the mathematicians in the room will agree, and that definition would be awesomely useful and work in all the cases. That is not the case. So in the mathematical problem S2E23, we're given 5-digit perfect squares, and we're asked to investigate or explain how many such perfect squares have the property that if one is added to each and every digit of that perfect square, yet another perfect square results. So which levers do we pull, which knobs do we turn and twist, and which buttons do we push in order to come up with precisely this simpler and related problem? Well, let's think about it together. Implicitly, or without stating so, we are dealing with non-negative, originally non-negative whole numbers, 0, 1, 2, 3, and so on. So one way, which lever can we pull, which knob we can twist, and which button we can push over here? Well, maybe we're thinking out loud. Instead of dealing with just non-negative whole numbers, we'll also include the negative whole numbers as well, -1, -2, -3. But once we kick this idea around, it's not really clear how does it make our life easier and how does it simplify the original problem and keeps the technical spirit of that problem intact in that direction. Next, we're dealing with squares, so it's natural to think about what about cubes or fourth powers or fifth powers or seventh powers or whatever the case may be. Here again, it looks like the process of increasing the perfect powers of a given non-negative whole number doesn't really help. We even think that is even more scary. It looks that we're making a problem more difficult instead of making it simpler in its perceived difficulty rating. Okay, fine, we throw this guy out, this idea out. What's next? All right, we said that we're working in base 10, so maybe switching from base 10 to base 17 or some other base will give us tactical advantage. We think about it and we don't really see how can that help. So what else is left? Well, right now, what else is left is the width of the perfect square at hand. We're dealing with the 5-digit perfect square. So here I'll write the original difficult to solve problem is a 5-digit perfect square is the problem that gives us grief, and we do not have any good idea of how to solve it. So maybe we can change just this one parameter. We just pull this one lever and we play with this one parameter called the width of the perfect square. And we think that somehow the width of the perfect square at hand is related to the difficulty rating of the problem, underlying problem, in such a way that the lesser or the smaller the width, the less difficult the problem is. So now we think, we're onto something. Our pessimistic, optimistic chain of reductions from the previous segment may be built around the parameter called the width of the perfect square. So now, instead of a 5-digit perfect square, what about 4-digit perfect square? What is going on with this idea? Is this problem simpler? Again, we think that perhaps it is simpler simply because the size or the number of 4-digit perfect squares that exist of, let's say, non-negative whole numbers is smaller. The number of such perfect squares is smaller, so we think maybe somehow it will make our work with the smaller amount of numbers easier. Does the step down in the width of perfect square preserve the technical essence of the original? Yes, all day long. Why not? If we have a 4-digit perfect square, we still can add 1 to each digit of that perfect square and demand that after that transformation, the new number is still a perfect square. Wonderful. Do we have any idea how to solve the related 4-digit problem? No, we don't. So what do we do next? We either get stuck or we give up, or because now we're the smart cucumbers, we know, okay, the scope reduction problem solving approach says keep rolling down, keep descending down the chain of perceived difficulty rating. And what is the next step in descending in the perceived difficulty rating? Yes, we play with the same parameter. We pull the same lever one more time, crank. So from 4-digit perfect squares, we go to 3-digit perfect squares. And again, we think about it. There are still less 3-digit perfect squares. Wonderful. But we still do not really see where this is going. How do we gain any competitive advantage by stepping down from the 4-digit perfect squares to the 3-digit perfect squares? Does the 3-digit perfect square problem relate to the original one? Yes, sure, all day long. We still can take our favorite 3 digits, add 1 to each such digit, construct a new number, and see if that new number is a perfect square. This is a perfectly valid mathematical problem. It preserves the technical essence or the spirit of the original 5-digit perfect square problem. And we, let's say, still cannot solve that problem. What do we do next? Well, some people who do not know about this particular problem solving approach may give up. Because we know about the scope reduction problem solving approach, we keep descending down the chain, this optimistic, pessimistic chain of reductions of the perceived difficulty rating. From 3, we descend to where? To 2-digit perfect squares. Again, is this problem simpler than the original? Again, because we said that the narrower our perfect square, the easier in some sense the related problem. And is this problem related? Yes, it is related, because we can still inquire. We can grab 2 base 10 digits, add 1 to them, and inquire if the new number after that transformation is again a perfect square. Doesn't really ring a bell over here. What do we do next? Keep descending down the pessimistic, optimistic chain. So we cannot solve the 2-digit perfect square, then according to the academic wisdom, there exists a simpler yet still related problem that we can or cannot solve. Let's find the problem and try to attack it. What's the next candidate for the problem that is simpler yet and still related? Well, it's one digit perfect square. And now we think, okay, if we cannot handle this problem, what will happen next? Well, the next problem, the next descent, the step in the descent will be 0-digit perfect square. And does that make any sense? Here it is interesting that many, unfortunately, especially younger students of mathematics, do not really know or understand that in mathematics, a number is an entity that is absolutely different from its representation. In other words, a number and its representation are two very different concepts. A number remains a number no matter how it is represented. And here we're inquiring about the possibility of having a valid and legal interesting mathematical problem in which a number is represented with 0 digits. Does that make any sense? Well, we think that it doesn't really make any sense. That is why we say this is not a valid or interesting mathematical problem, because we're thinking about a number that takes exactly 0 digits in this representation. Again, of course, we can play all sorts of games with symbols and everything, but in the nature of the problem here, we think that this is it. This is where the buck stops, so to speak. This is the terminal point. Here it's not a problem. So we back one step up and we now realize, the rock bottom, simplest possible related problem to our original problem is the 1-digit perfect square problem. And does that problem make any sense? Yes, it does. If we add 1 to such a digit, then we should get a perfect square. Can we deal with this problem? Well, if we cannot solve that problem, as I mentioned before, there is no hope that we will solve the original 5-digit perfect square problem. That is why it pays to dig our heels in, so to speak, and put up an academic fight and try to solve the 1-digit perfect square problem. Now that we managed to descend all the way down to the rock bottom simplest related problem together in this case, let us see if that is really the case. When we take on 1-digit perfect squares, then in some sense our reasoning that we carried out in the previous segment validates, because we do not really need any help altogether to write down all these 1-digit perfect squares, which are 0, 1, 4, and 9, and there are no other 1-digit perfect squares. And by manual inspection, we can carry out the experiment that is baked into the problem statement right away. So +1, I'll write down, let's say over here, +1 will result in what? Will result in 0 + 1 is obviously, I got too carried away, 0 + 1 is 1, 1 + 1 is 2, 4 + 1 is 5, 9 + 1 is 10. This is all base 10, no confusion. And how many perfect squares do we see as a result of carrying out add 1 to each digit of a given perfect square? Well, we see precisely only one perfect square, 1, because this guy right here, this forms an interesting pair. And just to make sure, let me write down over here, it gets a little messy, but you understand what's going on. 0 squared, 1 squared, 2 squared, and 3 squared. These are our candidates. And now let us go back to our theoretical portion of how this co-production problem solving approach works and inquire, did we solve the rock bottom simplest related problem? Yes, we did. The question was how many? And the answer is, bam, 1. There is only one digit perfect square that has the following property. Each one is added. If 1 is added to each digit of that perfect square, yet another perfect square results, and no other number, 2, 5, and 10, are not a perfect square, so these guys are out. Only this pair is in. And did we solve this problem? Yes, we did. But the question is, did we gain any useful insight that we can take and carry with us into the solution of the next slightly more difficult two-digit perfect square problem? The answer is not really, and some of our viewers will say, Roman, there are well-known cases in grown-up mathematics where a by hand or manual brute force enumeration, perhaps with the help of an electronic computer, is carried out, verified by the mathematical community, and once the mathematical community convinces itself good enough, then that proof, brute force, manual enumeration with the help of an electronic computer, is deemed to be a valid and legal mathematical proof, and voila, problem is solved. The answer to that question is yes, there are cases when a brute force, manual, electronic computer aided analysis of all the possible cases is carried out, it's verified, and it is a legal proof. Everything is wonderful, but the question is, what is the radius of application of such proofs? How do we take the tactical material, the insight in such manual enumeration proofs, and take it to another maybe related or perhaps even not related problem? What do we do then? Pretty much the only thing we can do is yet another, perhaps boring, manual case-by-case enumeration, and that's it. So that is the case. How do we take this observation to the two-digit perfect square problem? Well, some viewers will say again, Roman, there are not that many two-digit perfect squares. Let's do the same thing. But the question is again, when we climb up our pessimistic optimistic chain, we will be on the hook to do more and more manual enumeration work with three-digit perfect squares, four-digit perfect squares, five-digit perfect squares, and so on. This is not what we want to do. Maybe again, separately as a computer science exercise, yes, maybe we can write a little bit of, let's say, C code and figure out and answer this question. That is not the objective here. We're thinking, or we're trying to learn how to think like a mathematician, what a mathematician would do. Okay, here's one way. In order to switch from manual by hand case-by-case analysis, we can introduce one way to make a proof slightly more exportable or more shareable is to introduce more generic symbols and perhaps even quantifiers for all and exist, if P then Q, and so on. So what do we do here? Well, let's introduce more symbols that are not the specific numbers. If a perfect square, let's say we designate it with U, is one digit wide, then we will capture that number with only number of digits in base 10. These digits run 0 through 9. And we also know that precisely due to the nature of this problem, this corresponds to a perfect square, which means that for the number U, there exists yet another or a non-negative number, which when squared yields this number precisely over here. And then how do we convert? And notice here what we will be doing is applying the previously learned problem solving approach called equation. So how do we convert this spoken English into an equation? Well, when we say that 1 is added to each and every digit of a given perfect square, here there's only one digit. It's captured with U of number of units. So what do we write? We write U plus 1 must be what? It must be a perfect square. So how do we capture that? Well, it will be P squared. In other words, a number P raised to the positive second power yields this construct over here. But precisely because the square at hand is one digit long, it means that the number of units U can be replaced verbatim with the expression over here, S squared. So in other words, S squared plus 1 is equal to P squared. This is our conversion or translation from spoken language into what we think actionable mathematics of the information that's built into the problem statement if 1 is added to every digit. Now, when we look at this expression over here, do we see any actionable mathematics in it? The answer is yes, of course we should. In other words, if we add negative S squared to both sides of the equal sign, what will we have? 1 is equal to P squared minus S squared, and even though this is a recreational problem that deals with the elementary number theory, even still, this is a very favorable construct. Because why? Because now we know how to factor this expression. This is a difference of squares, can be written as p minus s times p plus s. And what does that mean? Well, here on the left-hand side of the equal sign, we have 1. On the right-hand side, we have a product of 2, in this case, of 2 positive whole numbers. Can either number be 0? No, of course not, because then we will get 0, and this is a contradiction. We have 1. 1 is neither prime nor composite, and as a separate exercise, you may try to think why 1 is not a prime, even though 100 or so years ago, some mathematicians actually treated 1 as a prime number. So now we have a product of 2 positive whole numbers that yield 1. How can this work ever? The only way this can work is when each and every factor in this product is 1. And also, by the nature of what is going on over here in this problem, we also think that the number p must be strictly larger than s. So in this case, this product over here translates into what? It translates into p minus s must be equal to 1. P plus s must also be equal to 1. What do we do with these equations? Well, we add them together, we erase s, and from this, what does it follow? It follows that 2p equals 2. From here, it means that p is equal to 1, and from here, it follows what? That s is equal to p minus 1. S is equal to, carefully, p minus 1. P minus 1, this is 1 minus 1 equal to 0. And bam, we managed to prove through a very, very super duper lightweight, barely touching it, lightweight number theoretic reasoning that the answer to the 1-digit perfect square problem is 1 precisely. Why? Because these two numbers, these two factors must be 1. 1 is neither prime nor composite. And then p is equal to 1, and s is equal to 0. And again, 0 is a perfect square, and if to each and every digit of that perfect square, of which there is 1, 0, we add 1, we obtain the number that is 1, and 1 is also a perfect square. And voila, now we not only solved the problem like we did before with the manual brute force enumeration of all possible cases, but now we think that we gleaned a certain insight into what is going on with the technical essence of the problem at hand. And in the next segment, we will take on, here we'll be moving up, we'll take on the 2-digit perfect square problem. Now that we managed to solve the rock bottom simplest related problem, shown over here, the 1-digit perfect square problem, not only we solved it, we think we managed to glean some insight that will be useful for us if we step up to the next slightly more difficult problem and try to take that problem on. Here again, some of our viewers will say, Roman, what are you doing over here with the 2-digit perfect squares? How many of them are out there? Well, not that many, agreed. 16, 25, 36, 49, 64, 81, and this is it. These are all the 2-digit perfect squares. Again, by manual examination, what is going on? There is only one 2-digit perfect square that has the property that if 1 is added to each and every digit of that perfect square, another perfect square result. And this is this dynamic duo over here. Again, in the +1 fashion, what will we have in this case? We'll have 27, not a perfect square. Here we will have 2 plus 1, 3, 5 plus 1, 6, 36 is a perfect square. This is 6 squared plus 1. We come here. Here we get 7. Here we get 4, 47. No good. Here we get 9 plus 1 is 0, carry 1 over. 4 plus 2 is 60 by the looks of it, 60. Not a perfect square, not a perfect square. 4 plus 1 is 5, 6 plus 1 is 7, 75, not a perfect square. 1 plus 1 is 2, 8 plus 1 is 9, 92, not a perfect square. Again, there is only one two-digit perfect square that has the property sought after. And here again, the following idea still stands. And unfortunately, I saw this in the previous about 7 or 8 years on Quora, that many people unfortunately do not understand that working in a brute force manual enumeration and manual examination case-by-case analysis is not the best thing to do, especially in your formative years. And yes, in grown-up mathematics, sometimes that is the only choice, because perhaps we do not really see what is going on. We do not understand how to approach a given problem in some other ways. So our only weapon of choice is a manual brute force case-by-case analysis. That is true. But again, in your formative years, you want to shy away from it. You do not want to look at all the problems in mathematics through the lens of brute force case-by-case enumeration, and you want to develop your ability to put together proofs that are more analytic in nature. And again, we want to try to learn how to think like a mathematician. So how would we approach this problem using the insight that we gained in the solution of the previous problem? Well, if our perfect square, S square, is a 2-digit number, then in base 10, how will that number be represented? Well, we'll write it as 10 times d for decimals plus u. This is a portrait of a 2-digit number, for that matter, any number, any 2-digit number in base 10, but our requirement, our constraint that number must be a perfect square. And how do we translate again the requirement baked into the problem statement that if 1 is added to each and every digit of a given perfect square, then another perfect square results? Well, we add 1 to every digit, and what do we have? 10 times d plus 1 plus u plus 1 must be a perfect square. This is how we translate it. Now what do? Do we see actionable mathematics over here? Yes, we do see actionable mathematics over here. We'll write 10 times d plus 10 times 1 is 10 plus u plus 1 must be equal to perfect square. We simply open up the parentheses. Now what do we see over here? Well, here in this string of symbols, we do recognize the portrait of our original perfect square. It is this usual suspect 10d, and it is u right here. So this formation right here with the plus sign, this formation right here is what? It's the synonym for s squared. So what do we have? S squared plus 10 plus 1 equals to p squared. You see 10 and 1. 10 and 1 is what? Is 11. Again, is equal to what? We add minus s squared to both sides of this equation. We obtain p squared minus s squared. Again, this factors s, p minus s times p plus s. Now we have choices. 11 is a number that this time happens to be prime. So now we can write the left-hand side of this expression of this equation as 1 times 11 is equal to p minus s times p plus s. We need to make certain decisions. Again, s is strictly positive in this case. The smallest s that can be is 4. So how do we partition the magnitudes of these guys? Well, p must be greater than s, because otherwise we get a negative number as a product, and here it's a contradiction. We have a strictly positive number over here. Also, where should we write it? can, let's say over here, can P minus S be greater than P plus S? In other words, what is the partitioning of these magnitudes of these factors in this case? Can this be the case? Well, here P is a positive whole number. We cancel it out. Carry this over here, and then what do we get? 0 is greater than 2s. 2 is a strictly positive number, so that means that 0 is greater than s, or in some sense we can even put the equal sign over here. And what does that mean? That means that s is less than or equal to 0. This is a contradiction in this case. In two-digit perfect squares, the number s, the smallest one, must be 4. So our number s sits between actually 4 and 9 inclusive. So in this case, this is a contradiction. This is not going to fly. So in that, what does that mean? It means that P minus S, we'll put it in parentheses, is less than P plus S. We'll remember this result, and that means that how do we partition these factors over these two factors over here? Well, obviously P minus S must be 1 and P plus S must be 11. Would you agree? P minus S is equal to 1, P plus S is equal to 11. We have two equations. Again, we already know how to solve them. Add them up, erase S. 11, just to make sure that you guys see that this is 11. 2 from here, it follows what? 2P is equal to 12. From here, it follows that P is equal to 6. P is equal to 6. And feeding, for example, I mean, we have two equations over here. We can pick any one. Let's pick the simplest in some sense, smaller numbers. P minus 1 is equal to S. P minus 1 is equal to S. 6 minus 1 equals to 5. So 5 is equal to S. Again, with our lightweight number-theoretic reasoning, we deduced in symbols in a more analytical way that in this case there is only one two-digit perfect square, such that, let us verify our work. 5 squared is 25. 25 is a perfect square. 5 plus 1 is 6. 2 plus 1 is 3. There are no carries. 36 happens to be a perfect square, which is 6 squared. Problem solved. Now that we understand how these things work with the two-digit perfect squares, we can keep climbing out of the hole and step up to the three-digit perfect square. The three-digit perfect squares already make my liver quiver, because the moment I think that I need to think about what these numbers look like, I don't want to do that. But we all understand that pretty much any positive whole three-digit number can be represented which way? In our case, that number must be a perfect square. So it will have some number for the hundreds. We'll designate it with H for hundreds, plus 10 times D for decimals, plus U for units. Here we will demand that the number H is not 0 for it to be a legitimate three-digit number. And we already understand how to proceed further. We convert using the equation problem solving approach that we just studied in the previous episodes. We convert the spoken language of if 1 is added to every digit, blah, blah, blah. So how do we obtain the equation over here? Well, we'll write 100 times H plus 1, increment the number of hundreds by 1, plus 10 times number of tens incremented by 1, plus U incremented, number of units incremented by 1, still comes out to magically a perfect square, p square. What do we do? Do we see actionable mathematics in here? Yes, we do. We open up the parentheses, and what do we see? 100 times h plus 100 times 1 is 100, plus 10 times d plus 10 times 1 is 10, plus u plus 1 is p squared. And what do we see? We want to find the portrait of s squared written in its decimal expansion. This, by the way, is a little theorem. Depending on the course that you take, it may be mathematics or computer science. But what do we see over here? 100 times h, 10 times d, and u. So this suspect plus this suspect plus this, I'll grab the plus sign this way right here, is a synonym for s squared. And what do we have in the end over here? S squared plus 100 plus 10, I'll write it in a revealing way, plus 10 plus 1 is equal to p squared. So now in our three-digit problem that we're dwelling right here, we are using our cumulative insight that we gained during the solution of the rock bottom simplest. The next slightly more difficult problem, what do we have? 100 plus 10, 110 plus 1, 111 times is equal to, I'm sorry, again, p squared minus s squared. We understand we add negative s squared to each side of this equal sign. We factor it in a predictable way. We already know what's going on. Times p plus s. We proved all our analysis for the distribution of magnitudes of these two factors. 111 turns out to be not prime over prime. It factors which way? 3 times 37 is equal to p minus s times p plus s, like so. And what do we see now here? Again, due to our work that we did in the previous segments where we analyzed the possible distribution of the magnitudes of the factors involved, what do we have? We have p minus s must be married to 3, and p plus s must be married to 37. These are our two favorite primes. So from here, what do we do? Do we see actionable mathematics? Again, we add these two equations together, erase s. We have 2 times p equals 2. 37 plus 3 is 40. Another nice even number. From here, it follows what? P is equal to 20. P is equal to 20. And what do we have for s? It means that from here it follows that p minus 3, again, we have two equations to play with in order to recover the value of s. We choose to play with the smaller numbers. So then s is equal to p minus 3, that is 20 minus 3 is equal to 17. This is our s, this is our p. And what do we do now? Again, we claim that the solution of this problem is the following. There exists only one three-digit perfect square of a whole non-negative number, such that if 1 is added to each and every digit of that square, yet another square results. So here we have our candidate as 17. Let us do it over here. Perhaps we're here. No, let's do it here. 17 squared is equal to what? It's 289. This is our square of the number s. S squared, s is 17. 17 squared is 289. So now we add 1 to each digit of that square. So what do we get? 9 plus 1 is 10. So we write down 0 and we carry 1. 8 plus 1 is 9. 9 plus 1, again, 0. And what do? Carry 1. 2 plus 1, by the rule, plus 1 carry. 2 plus 2 is 4. 400. And 400 translates into what into our case? Exactly, it translates into 20 squared. There we go. S is 17, its square is 289. When 1 is added to each and every digit of the perfect square shown over here, yet another perfect square, 400, which is 20 squared results. Our work checks out. Now that we understand what is going on, we can keep climbing out of our hole here and take on the 4-digit perfect square problem. With the 4-digit perfect square numbers, we already understand what is going on, so we jump to the work right away, and we write down a perfect square that is 4 digits wide as follows. It will be 1000 times k plus 100 times h plus 10 times d plus u. We demand that k is not 0 for it to be a true 4-digit 1, 2, 3, 4, 4-digit number. This is any whole positive number will be written that way. In our case, the constraint is a square. How do we translate the fact that when 1 is added to each digit, then a new square results? Then we will write down it as 1000 times k plus 1 plus 100 times h plus 1 plus 10 times d plus 1 plus u plus 1 is still a p square. Once we open up the parentheses and multiply 1000 by 1, 100 by 1, 10 by 1, and 1 by itself, we also recognize the portrait of the square, this usual suspect in here, and we will have what? S squared plus, let's count carefully, 1000, 100, 10, and 1. So it will be 11,011 will be a p square by our demand. We already understand what's going on. 1111 turns out to be not prime. It factors over primes as 11 times 101. That's a separate exercise. For now, we take it as known ahead of time. Minus s squared. Again, partition it into two factors, p minus s times p plus s. Recall our previous analysis. This analysis stands. We still have a strictly positive number, in this case greater than 1. Pum, pum, pum. We understand what's going on. So now p minus s will be what? Married to 11. P plus s married to 101. So from here it follows what? It follows that 2 times p will be, oh my god, 112. From here it follows what? P is equal to 56. 56. And from here it follows what? Again, we'll take the simplest in some sense, work with the smaller numbers. 11 is less than 101. P minus 11 is s. So here s is p minus 11. 56 minus 11 is 45. This is s. And this is our answer. We claim that over the set of non-negative whole numbers, there exists only one 4-digit perfect square, such that if 1 is added to each and every digit of that number, then another perfect square results. We check our work. And how do we do that? Well, s squared in this case will be 45 squared. And what is 45 squared? Anyone is here to guess? Exactly, 2025. And that is the year in which this episode is shot, 2025. Add 1 to each number. Plus 1, 6, plus 1, 3, 36, plus 1, 1, plus 1, 3. And what is this? 3,136 is a perfect square, and it happens to be 56 squared. So this is actually squares nicely against our computations, and there we go. There exists only one 4-digit perfect square with the property requested, and that perfect square is 2025. After it undergoes the requested transformation and every digit of that perfect square is made heavier by 1, let's say, kilogram or whatever, then another square, perfect square results, and that perfect square is 3136. Now that we accumulated all sorts of beautiful wisdom while climbing out up our pessimistic optimistic chain, there exists a simpler related problem which you can or cannot solve, blah blah blah. Now we come back to the original problem, and now we can take it on. Lastly, once we come to the problem with 5-digit perfect squares, then we already cut to the chase. We understand what is going on. We express our original perfect square as the following sum: 10,000 times, let's say, t for 10,000 plus 1,000 times k plus 100 times h plus 10 times d plus u. We also demand what? That t is not 0. We understand that now when we apply the transformation to this perfect square that is baked into the problem statement, we basically take every digit over here. T becomes t plus 1, k becomes k plus 1, h becomes h plus 1, d becomes d plus 1, and then u becomes u plus 1. This whole beautiful mess becomes still p squared. We demand that this is a p square. Once we multiply all these parentheses out, then we reassemble the portrait of this number over here. So what will we have? We will have s squared plus 10,000 plus 1,000, 11,000, 11,100, 11,110, 11,111 plus 1. So 11,111 will be p squared, which means that 11,111, which factors over primes as 41 times 271. That can be done. That's a separate exercise, but that's not the point here. It can be represented as p squared minus s squared, and this is p minus s times p plus s. And then from here already we reuse the previous analysis. We write down the following pair of equations. P minus s will be 41, and p plus s will be 271. So from this pair of equations, what do we get? Again, we sum them up, we erase s, we obtain an expression 2 times p will be what? 312. From here it follows that p is equal to what? 150 plus 6, 156. This is our first candidate. And if p is equal to 146, between two expressions, again, between two equations, we choose the one with smaller numbers, because, again, size somehow we correlate with difficulty rating. The smaller, the simpler. So in this case, p minus 41 becomes s. So p minus 41 is what? 156 minus 41 comes out to what? 115. This is s. This is our answer. And again, due to a very lightweight number-theoretic reasoning, we proved that the answer to the original problem is there exists only one 5-digit perfect square of a non-negative number, such that if 1 is added to each and every digit of that perfect square, another perfect square results. So how do we verify our work? 115. So we write it down over here. S squared, which is 115 squared, comes out to 13,225. Again, at this point, this is not the mathematics. This is just arithmetic, computational calisthenics. So here we add 1. What do we have? 5 plus 1, 6. 2 plus 1, 3, no carries. 2 plus 1, 3, no carries. 3 plus 1, 4, no carries. 2 plus 1 is 2, 24,336. 24,336. And lo and behold, this is precisely 156 squared. And this is precisely, this little piece right here, precisely is the answer to our problem. Exactly one 5-digit perfect square. 13,225, which is a square of 115. Has the property that if 1 is added to every digit of that perfect square, another perfect square results. The result is 24,336, which is a perfect square of the number 156. That is, 156 squared is 24,336. Again, we should step back, reflect on our problem-solving experience, and understand that the small, light caliber arithmetic work over here is not real mathematics. The real mathematics was the idea to face a difficult and challenging problem and they realize, aha, we cannot attack it head on for whatever reasons, and here is one way to deal with the problem. Reduce this problem in a series of steps to the rock bottom, simplest possible related problem in this case. Not only solve this simplest, rock bottom, simplest related problem, but also gain a useful insight which we can take with us into attempt to solve the next slightly more difficult problem, the next slightly more difficult problem, and on and on and on until we manage to solve the original problem. This is it for the problem S2M23, and we will look at the next challenge next. In our next challenge, the mathematical problem S2M24, we are challenged or asked to find or construct the locus of points on a sphere that of which every point is equidistant from 3 given fixed points on that sphere, and we're interested, of course, in the most non-degenerate case when no 2 points with respect to each other are antipodal on a given sphere. And again, by now we understand that we're not interested in just an answer, but we're interested in a story of how that answer comes around. And we also saw in the previous several segments in this episode how the story develops. How do we put together a story of how and why, which leads us to this specific answer. Also in this particular problem, we again are interested in your side of the story of why the answer to this mathematical problem is what it is. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2M24.